Morning. Can you hear me? Can you see the blackboard? Can you hear me? Can you see the blackboard? Okay, thank you, Killian. Now, yesterday, we talked about changing our strategies from using the equations of motion Then we use Newton's laws. And finally, yesterday and the day before, we learned how to deal with the work energy. We have the work energy theorem. We have something different. We need to deal with it now, which is the momentum and its application is like impulse and what's the relation between the momentum, which is the linear momentum. That's all for the linear motion. We have the first exam, these things. The second exam will cover these things. Then we have the rotational motion. And some applications. So the final will cover these chapters. Today we'll talk about the momentum, the rotational motion. We'll cover again these topics. Now we have a new quantity. We need to study new quantity. We need to study also applications and physics relations for this quantity. Starting by Newton's second law, as we know it from before, F is equal to m multiplied by the acceleration. F is a vector quantity. It gains its property from the acceleration. Now, what is the acceleration? The mass is the mass. It is constant. The acceleration, we have the average acceleration, which is delta V over delta T. If we need to find the instantaneous acceleration, it will be m del d v over dt, which is the first derivative in math. But we will not deal with it as a first derivative. It is just a small change in the velocity within a small change in time. Now, any change in the velocity, we can write it like this. This is the mass. This is the change over the change in time applied on the velocity. The mass will not change. If we apply a change on the velocity, it will not affect the mass. So we can put the mass inside here. So it will be like this. The change over the change in time of the mass multiplied by the velocity. This is just a number, the mass. Now we have a new quantity derived from the force. And we can derive the force from that quantity. This quantity, mv, we need to define this quantity as the momentum. The moment or the linear momentum. Linear means the motion in a linear line, a linear path, which is a straight line. The momentum has a sample p, which is a vector, is equal to the mass multiplied by the velocity. It's a velocity of the mass. It's a vector quantity, as we see. Now, the force, we have the average force, which is delta over delta, or we have the instantaneous force, which is d over d, which is a small change. Now this momentum is a vector quantity, and we can write it as a vector. P is equal to Px, just as we did for the any other vector. I hat plus Py, J hat plus Pz, K hat is Z direction, but we will not deal with this direction. It's enough to deal with two dimensions. You are seeing that in page number 1. And Px is equal to the mass multiplied by Vx, which is the velocity in x direction, I hat, plus the mass multiplied by Vy in j direction and the z direction. It is simple. Px, it is the momentum in x direction, which is mv. The momentum always, it is mv. In x direction, mvx. In y direction, mvy. We will solve examples on that. What is the units of the momentum? The mass has kilogram. Velocity, it is meter over second. This is the units of the momentum. If you look again at Newton's second law, so we can see that F is ma, which is, this is the final relation, which is delta over delta T mv. This is the relation, which is equal to delta over delta P T. mv is the momentum P. So now we have a new relation between the force and the momentum. We will see what is the momentum mean. But now let us see this relation. The force is the rate of change of the momentum with respect to time. This is the average. The instantaneous, we need the time and the momentum to go to small changes, which is dp over dt. The first derivative of the moment. The second page, now we have this relation for the moment. The second page, now we need to know what is the moment. It's a vector quantity, okay? If we have this experiment in our minds, this is a mental experiment, and we can do it. You can throw up a small ball to me, and I can catch it easily. But if you throw, for example, a chair, it's difficult to me to control catching because the chair has mass more than the ball. If you remember, we have the kinetic energy is equal 1/2 mv squared. But now the momentum is equal to mv. It is almost the same, but we have a square value and we have a vector quantity for the momentum. There is a strong relation between the kinetic energy and the momentum. The kinetic energy is energy, the momentum is not energy. It is the amount of motion of that object. For example, the motion of the train, it is not the same as the motion of that electron, what we found, its kinetic energy. Also, now we will see an example, the difference between the momentum of a fast bullet and a slow train, I think. Yes. This is my example, just to know what is the difference between the big and the small momentum. If we have a small ball, small means small mass. small mass ball, and this is me. How I'm trying to stop it. It's easy. But if you a tire for a loader, for example, this is a big mass. Whatever its velocity, in this case, I will not be able to stop it because mv, it has capital big M. In this case, look here. In this case, the mass is big. The velocity maybe it is small. So the momentum is big. In this case, the mass is small, you cannot see it. And the velocity is maybe the same like this one. So the momentum will be small, will not be big. Let us solve. Any question about momentum in general now? Online? Because I will solve an example, simple example. The relation is simple. P is equal to mv. That's it. We know that mv squared over 2, which is the kinetic energy from before. We have 2 experiments. A bullet with mass, small mass, is equal to 0.04 kilogram. It is smaller. And its velocity is big, which is almost 400 meters per second. And we have a train with its big mass. Remember the electron and the train example for the kinetic energy. The mass almost 30 tons or 30,000 kilograms. And its velocity just 10. We have small velocity. Almost 10 meters per second. What is the momentum? P. We have a motion in one dimension, okay? Assume that the train moves to this direction, to the positive x. There's no matter, okay? This is just multiply them by 0.04 multiplied by 400. In positive x direction, it will be equal to how much? Just 16 kilogram meter per second, just like that. What about the train? The momentum for the train is equal to the mass, which is 30,000 kilograms, multiplied by this small velocity in positive x direction. It's simple to be found. It's 300,000 kilogram meter per second. I cannot stop any one of them by my hand. For example, the bullet will go through my hand and go away because it is small and it is fast. The train, if I need to stop it by my hand, it has a very huge momentum. I cannot stop it. Okay. If you need to compute the kinetic energy, I'll compute it to you. It does not compute here, compute it here, yes. The kinetic energy, we know the relation. It's half mv squared. Look here. This is a good connection. 1/2 mv squared multiplied by m and then divide over m. It will be m squared v squared over 2m. mv squared, it is p but squared over 2m. There is a direct relation between them. So the kinetic energy in this case will be p squared over 2m, which is the same relation, half mv squared. Now, 16 squared over 2, how much m? 0 point, no. The kinetic energy for the bullet is equal to 3,200 joules. The kinetic energy for the train the momentum square, which is 300,000 square over 2 multiplied by its mass, which is 3 and 4 zeros. Yes. The kinetic energy, it is 1 million and a half joules. It's 1.5 million joules, but here it is just 3,000. Yes, it is fast. It is. Its mass is very low. It is the same kinetic energy law. There's no difference. So, any question about this line? So the momentum, as you see, depends on the magnitude and the direction and its unit. Okay, now I finish everything about momentum, the concept of the momentum, but we have many applications on that. The momentum, it is the velocity of a mass. Now we have a different quantity, another quantity. The other quantity, the next quantity, which is the impulse. Now, by doing this example in page number 3, if we have a ball with mass equal to 0.5 kilogram, it's simple. Has a velocity v initially equal to 5 meters per second. It's a soccer ball. Now, we kicked it. One of us kicked it, and its velocity later, v2 is equal to 8 meters per second. During a time, delta t is equal to 1.2 seconds. He's still pushing it for a long time, which is 1.2 seconds. Yes. Okay. Now this is the ball. Initially, and this is the ball finally, but its mass is the same. There is no change on its mass. Later, we will study, maybe tomorrow, yes, tomorrow, the change in mass in the rocket example. Its velocity here was 5. Its velocity here became to be 8. Here it was 5. Do we have a change in something? Who can tell me? Yes, we have a change in the velocity. Okay, we have change in the velocity. Any new quantities depends on the velocity. Yes, we have the kinetic energy. Yes, you're right. But I don't need to study it. Now I'm talking about the momentum. But it's a good point. We have a change in kinetic energy, which is K2 minus K1. What is this quantity equal to? The change in kinetic energy. Simply, it is the work. Remember that yesterday or the day before? The work is an energy convert the system from a situation to another, from a state to another state. Okay, what we have also here, we change the momentum. We have the initial momentum is equal to the mass, which is 5. The mass is, no, 0.5, multiplied by the initial velocity, which is equal to 2.5 kilogram meter per second. Then the momentum finally, or P2, became 0.5, which is the mass, multiplied by the new velocity, which is equal to 4 kilogram meter per second. Do we have any change in this quantity? Yes, we have. Let me just compute the kinetic energy to find the work. We know the kinetic energy relation, it is 1/2 mv squared. This is 1/2. The mass is also 1/2. V squared, the first velocity, 25. So the initial kinetic energy it's 6.25 joules. The final kinetic energy is 64, the same thing, 16. So this will be equal to 9.75 joules. This is equal to the work. Agree with me? Okay. We have a change in momentum. Delta P is equal to P final minus P initial as vectors. Okay. It is equal to 4 minus 2.5, which is equal to 1.5 kilogram meter per second. Okay. Just as we did with the wall, and any change in the kinetic energy or in the potential energy, we say the work is the tool or is the language to change the energy from shape to shape. We now change the potential. No, not the potential, I'm sorry. We change the momentum from case to case, from 2.5 to 4. Is it a work? Is the change in momentum? Is it the work? No, the work is energy, it is in joules. The change in momentum, we name it impulse. So the impulse for the momentum, the work for the energy. So this is equal to something named J, which is the impulse. So the impulse is just the change in momentum. Another thing, let us continue with energy, momentum, comparing. We know if we divide the work over delta T, what is this quantity equal to? It is in the, not the previous lecture, the lecture before. What is the work divided by the time? It is measured in what? This is equal to power. The energy divided by the time. We have the time and we can find it, the power. So the work is 9.75 divided over 1.2. The power is 8.125 watts. The power of your leg when you shoot this ball and increase its velocity from 5 to 10, your power now is 8.125. Okay, this is the work done over the time. What about the impulse? Impulse over the time. We know the impulse, what is it? It is delta P over delta T. What is delta P over delta T? We just talk about it. For this one, it is the force. So, impulse happened during a time will give us the force, which is delta P over delta T. Okay, 1.5 over 1.2, it is 1.25. What is the units of the force? It's newtons. In physics in general, everything is related together. We did the same steps for the energy and for the moment. Cannot see. Enough. Right. Any question about this? The impulse, it is the change in momentum without the time. If you divide over the time, you will compute the force. Any question about this point? We have an example now. Another example. We have 20 pages for this our lecture. 10 of them today and 10 of them tomorrow. And our lecture will be just maybe an hour. I think you will be more happy to finish your physics book without spending 2 hours this summertime. Previous summer, there is no opportunity to teach online like this. There's no cameras and there's nothing. So I have to prepare videos from YouTube and record some videos to discuss this material. It was very miserable. But at the end, they could solve and understand what this is. Now the other example, it is very common example. If we have a wall and we have a ball, this ball is moving to the positive x direction, as you see here. Its mass, its velocity v1. Then it hits the wall and reflects by v2 or final velocity. Okay. The mass of this ball is equal to 0.2 kilograms. V1 is equal to 20 meters per second in positive x direction. Okay. V final, which is V2, yeah, it's a vector, okay. 15 to the negative x direction. I need to compute many things. And the time period is equal to, it's very fast, 5% of a second. We need to find the momentum initially and the momentum finally. It's simple. and multiplied by V. That's it. It is 0.2 multiplied by 20. I had, so it will be over 5, it will be 4, I think. Yes. 4 I had meter per second multiplied by kilogram. We have a kilogram. B finally, the mass, the same mass. We don't lose any mass during the interaction. This is an interaction. By 15 minus I had, this is equal to 3 point, just 3, yes 3, or 3 to the negative x direction, kilogram, meter per second. Oh. Okay. I gave you the time. Now we have a change in momentum. We can find the impulse. We can find the force. We can find anything, even a kinetic energy and the change in kinetic energy. And we need to discuss where is this loss in energy. Okay, the third requirement. The force. Let us compute the 1, 2, delta P. This is the third requirement, which is equal to the impulse. It is P final minus P initial, which is equal to 3 with minus sign. I had minus 4 I had. It will be negative 7 I had kilogram meter per second. It's simple. What about the force? The force. After finding the force, we will talk about it. It is equal to J over delta T as a vector. Also, it is equal to delta P, which is the same, over delta T, which is equal to 7 over that time. It will be minus 140 newtons. The negative sign means that the force is to the negative x direction. Who did this force? Is it the ball or the wall? It is the normal force from the wall on the ball. This is the force. Okay. What else? The kinetic energy and the changing kinetic energy and the work done by the wall. The kinetic energy initially. It is important to deal with the kinetic energy because we have the collisions after a while, and we have to deal with the kinetic energy. It is equal to 1 over 2 multiplied by the mass by the initial velocity squared, or v1 squared. This is equal to 1/2. The mass is how much? 0.2, yes, right? Thank you. And the velocity is 20 squared. We didn't deal with the vectors I, j, k, how to multiply them. But if we need to multiply 20 I by 20 I, it is 20 by 20 I multiplied by I, like this. I multiplied by I, it is 1. 2 vectors, it is cosine theta between them. Cosine theta between them. I in this direction and the other I in the same direction. Cosine theta between them. Theta is 0, cosine theta is 1. So it is 1. So here, when we need I, need to square the velocity, I square, it is 1. It is not the square root of minus 1. I. We are not dealing with this. It is the direction. So the kinetic energy, initial kinetic energy, is equal to which is 40 joules. By the same way, the final kinetic energy is equal to 22.5 joules. There is no negative sign because negative I multiplied by negative I, the negative with the negative will give us positive. I multiplied by I, it is cosine 0, which is equal to 1. Okay? What is the change in kinetic energy? Delta K, that minus this, which is equal to negative 7.5 joules. It is negative. Do you remember the work of the friction force? It was negative work because the friction force it's the direct to the opposite direction of our motion. Right. We have a negative change in kinetic energy, which is a work at the end. It is the work done by the wall. This work is negative. Is there any friction force here? No, we don't have any friction force. We just have a collision and reflection, that's it. The negative work or the negative change in kinetic energy means we lost energy. That's right, because our velocity later less than our velocity before. In this case, this collision doesn't conserve the kinetic energy. The kinetic energy lost here. And what is the shape of this work, the negative work? You can see here there is a deformation of the shape of that work. This will consume some energy. Assume this ball is a glass, it will be broken. It needs energy, then the energy will be gone. But it is a rubber. It is not broken. Okay. The deformation consumes some work. There is a heat here on the wall and on the ball. So we have some heat from that energy. Also, we have a sound. Okay? So we don't have a perfect experiment. Always we have negative work in our experiments. Any question about this? Now I will talk about the conservation of momentum. The momentum should be conserved during any interaction in a closed system. If we have a closed system, the energy should be conserved, the momentum should be conserved. Now, if we have two persons, me and you, we apply a force. This is A, this is B. We have a force from A on B. This is from A on B. We have another force like this from B on A. assume this force is 10 and this force is 7. A person will win, okay, because he will push the B person. But if both forces are 10 and 10, for example, if I push the wall by 10, then the normal force will be the same, 10. This is Newton's third law. So we have the force from A on B is equal to the same magnitude as the force from B on A, but its direction is opposite, right? But we know from before that the force, too much before, just this lecture. The force is the change in momentum over the change in time. It will be the same from A and from B. If I apply a force on B, then I will change his velocity. So my force A on B will change the momentum of B. If you apply a force on a ball, and there's a force between you and the ball, you will change the other object momentum. This will be also negative, the change. The object will change your velocity and your momentum. If you receive a ball, it will change your velocity. B, A, over delta T. But the interaction time is the same for you and for the other object, for A and B, the same time. If we move this one to this side, it will be delta T, delta PA will be positive, plus delta PB over delta T over delta T. We have delta over delta T is common, we can take it outside. It's PA plus BB. When we bring this to this side, the opposite side will be 0. When we move this to here, it will be B0. So now look. I'll put it here. I'll tell you something important now. We have delta over delta T of PA plus PB is equal to 0. I can multiply and divide by delta T over delta T here. It is 1. I can multiply it by 0. I'm okay. Delta T by 0 is 0. Delta T by 1, it is delta T. So I can put it 0 over delta T. Or I can assume it like that. 0 over 1, this over delta T, multiply it by this, like this. So delta PA plus PB multiplied by 1 is equal to delta T multiplied by 0, which is 0. Now I have a change in something is equal to 0. The change of the color of this lamp or camera is equal to 0. The color of this lamp is red. After 2 seconds, it's red. The change in red between 2 seconds is 0. It's red minus red. The change is 0. That means the momentum for the system initially at a state is equal to the momentum for that system finally as a vector in x and y. But we will deal with it in just in one direction, our example from now on. So any change, for example, this means if this is our system, has a momentum for the system is equal to the momentum of A plus the momentum of B. It is not changing. So the momentum of our system initially is equal to the momentum of our system finally. There is no change of the momentum. This is very important. The momentum is not changing, means delta P is equal to 0 or P final equal to P initial. Also, we have another relation from before, if you remember it. Delta mechanical energy is equal to 0, means the mechanical energy 1 is equal to mechanical energy 2. This means the energy is conserved, the mechanical energy. This means the momentum is conserved. Conserved means it doesn't change its magnitude by the time. Any question about this? Now we have two important postulates: the conservation of energy, the conservation of momentum. A small thing, you know that the momentum is a vector, which is equal to Px I hat plus Py j hat. It is considered, means that Px will not jump. For example, if we have here 5 and here we have 4, we will not see one momentum from here jump to the y direction to make this 5 and this will be 4. This will not happen because the x direction is separated from the y direction. This means Px initial is equal to Px final. Also, Py initial is equal to Py final. You will see the momentum in y direction is 4 always. In some example, for example. Okay, so don't think that the total momentum will change between x and y direction. The x direction will stay the same, the y direction will stay the same. Correct. Okay. I think there is an example now. Yes. Any question about momentum, impulse, force, energy? We have an exam this Friday. It will be just like the previous one. You can take the exam anytime. Just tell me your best time. I will open it at 4. Okay, our example now. We have an idle and the bullet system. Page number, how much? It's number 2 now. Okay. We have the mass of the rifle is 3 kilograms, which is capital M. The mass of the bullet is 0.0055 grams. The velocity initially, we are here initially. V capital for the rifle is equal to 0 meter per second. And V for the bullet is equal also 0. If I ask you to compute the momentum of this system, the momentum of this system now, it's capital B for the system is equal to the momentum of the rifle plus the momentum of the bullet. It's MV, M plus MV. It will be 0, right? So the initial momentum is 0. I told you the momentum should be conserved. So at any time later, your momentum should be 0. Even when the bullet is going fast, because the rifle will go backward with its mass. Okay, after shooting. Now, this is finally. The mass, capital mass, is still the same, 3 kilograms. We have the rifle and we have the bullet with its small mass, 0.005 kilograms. But its velocity now is equal to 300 meters per second. Here, after shooting this bullet, the gun machine will go backward. You know, I think you saw many of these videos when somebody doing this, the rifle going backward. Also, the cannons go backward. What is the velocity for the rifle fire? It's a big V. It's simple to find that. It is by doing P finally is equal to P initially, which is equal to 0. It is a vector quantity, just like what we did in the previous lecture, when we compute the mechanical energy is equal to the kinetic energy plus the potential energy and so on. Okay, what is this equal to? The mass of the rifle multiplied by its velocity as a vector, plus the mass of the bullet multiplied by its velocity as a vector again. These chalks should produce too much dust because the other chalks, their font is very thin. You cannot see it from the camera. We have M, V small, square. No, not square. They are not doing good there. Okay, 0 is equal to the mass, 3. The velocity of the rifle, I don't know it. I need to find it. Plus the mass, 0.005. The velocity, 300. Positive x direction, which is I hat. All of this is equal to 0. Okay, show me what we can do. We have 0 is equal to 3 V of the rifle finally, plus 300 multiplied by this. This will remove this. This will be 1.5 I hat. Okay, kilogram meter per second. Okay, I need to find V. Simply put this to the opposite side. It will be negative 1.5 I is equal to 3 V rifle finally as a vector. Okay, then divide over 3. Okay, then this will be equal to negative 0.5 I hat equal to V rifle finally. Is rifle right word? Is it rifle? Okay, thank you. Now it is negative 5 I have, or negative 0.5 or negative half. So V rifle finally is equal to 0.5 in the negative I direction meter per second. So the rifle, the gun machine, will go backside by that velocity, half meter per second. Look, the bullet goes fast, 300 meters per second. The rifle, because it is heavy, go backward, half meter per second. If your little kid run to you, little kid or little brother, I'm sorry, I'm thinking about myself, run to you and he jumped to you, his velocity is relatively high, but when he jumped to you and you catch him, you will go back by a little velocity because your mass is very big compared to his, or his momentum is not enough to change your velocity in large amount. Any question about this? Now we use the conservation of momentum to solve an example. We can use also the conservation of energy to solve this example, but we will do that later. We have another example. We spent 1 hour. I am sorry, I'm too slow, but okay, we have a collision between two balls. We have a ball A and a ball B. The mass of this ball, MA, is equal to 0.5 kilogram. MB is equal to 0.3 kilogram. This velocity, PA, initially 2 meters per second, I had the positive direction. And VB initially is equal to 2 meters per second to the negative X direction. We are dealing just with one direction, okay? There is a collision, then a reflection. We know that. Okay. What we need to find? Find the initial momentum. P initially. For all the system, it is PA plus PB. It is equal to the mass multiplied by the velocity. It will be half multiplied by 2, it is 1 I have. Plus the mass multiplied by the velocity, it is 0.6 with a negative sign. Negative 0.6 I had. So the momentum initially equal to 1 minus 0.6 is 0.4 in I direction to that direction, kilogram meter per second. It should be conserved or not, I will say now. We need to find VA finally. Okay, the momentum finally, it should be equal to the momentum initial, which is 0.4 I have. And this is equal to the mass of A, which is 0.5, multiplied by VA finally, plus the mass of the momentum of B, which is the mass, is 0.3 and its velocity, it's given 2 meters per second. After the collision, the ball beam reflects by 2 meters per second. This is V. B final. This is given. Okay, we can find that in I hand. So 0.4 is equal to 0.5 multiplied by VA. This by this is plus 0.6. All of them in I direction. Okay, I need to tell you we are dealing with just in one direction. Now put this in this direction and to the opposite side. It will be negative 0.6 plus 0.4 is equal to 0.5 VA finally. This is negative 2.2 over 0.5 is equal to VA finally. This will be equal VA finally is equal to 0.4 meter per second in negative I direction. We have negative sign. The given table, you can find the momentum initially, the momentum finally for the first object, the second object for the system, and the change in velocity. But you will find their change in velocity, there is no relation between the change in velocity between A and B. There is no, the change in velocity is not 0. But the change in momentum is 0. Look at the last column in page number 3 here. We have negative 1.2 plus then we have positive 1.2. If you add them together, the total is 0. The change in momentum, the total momentum is 0. This is the important thing, the momentum and the energy. We don't need to do anything with the velocity. It's not important. Okay, this collision name has a name. We have 2 types of collisions. Actually, 3 types. We have elastic and inelastic, and we have one between them, which is semi-elastic or semi-elastic. But we need just to divide them to 2 categories, which is elastic and inelastic. In actual life, we don't have the ideal elastic collision. Always we have missing energy. Any question? I'll start talking about collisions. We will use the momentum equations and the kinetic energy equations, just like that. Now we have the collisions are 2 types. This is collision. Elastic and N. In the elastic collisions, delta P of the system before and after is equal to 0. And the change in kinetic energy is equal to 0. That means P before or initially is equal to P finally. And kinetic energy initially is equal to the kinetic energy finally. In non-elastic or inelastic, the momentum is concerned, it's okay. Means P initial is equal to P final. But the kinetic energy is not. If the kinetic energy initially is 10, later will be 7, 5, and so on. And missing kinetic energy, as we said from before, it may be a heat, sound, and deforming of the object shape. The deforming of the shape, assume we have two balls of clay, for example. When we throw them together, they will stick together. This will change their shape, and the system will change its property. We have a new object. This we have sticky and non-sticky. You will see that in the lab also. Now I will put the equations of this in this page. You will see I will write the equations. Here, initially and finally, assume that we have two objects. They are moving just in x direction. I will not make it complicated to you. And we can study them in x and y and in z direction, also in t dimension with 4 dimension and general relativity and special relativity. We deal with 4 dimensions, but here we will deal just with 1 dimension. Okay, we have 2 objects. The first one and the second one. The first one has its velocity. The second one has its velocity. Initially, before the collision, it will be equal to the first mass plus the second mass multiplied by their velocity. Finally, this is the total momentum of the system before the collision, initially. This is the total momentum finally. All of them in x direction, so I will not put a vector sign on the velocity. The mass will not change, the velocities will change. So I will put it v1 prime, v2 prime. It's okay. In your solution, if you need to write it before and after, it's okay. What about the kinetic energy? It is simple. 1/2 m1 v1, just like the momentum, but it is squared, plus 1/2 m2 v2 squared. This is all before. Is equal. There is no place. I'll put it here, or I will just shift it to the left a little bit. This is the final, and this is the initial. 1/2 m1 v1 squared plus 1/2 m2 v2 squared. This is initially, as we said, is equal 1/2 m1 v1 prime squared. Look, we have many things. It's disgusting. M2 v. When I was in your place, I have the same problem. Prime squared. Because of that, later, I don't care about prime and prime. Just I put finally here. I solve my problem initially total. And then I go to solve it finally totally, then compare them together. I will not put prime before, after, and that's it. This is for the elastic collision. Any question about this? For inelastic collisions, we have many forms. we have different many forms of that. For example, the deformation of the shape of the ball. If we throw a glass, a cup, to a stone, the cup glass will be broken. We have deformation. We have many shapes. For example, of inelastic collision. But we will study one of them, which is when the two objects stick together. If we have M1 we have a black chokes, this will be like that. If we have another mass, M2, after the interactions, like a chemical interaction, there will be just like one object. This is M1 plus M2. We need to deal with them like this. The momentum is conserved. Okay? So the momentum initially, it is M1, V1 plus M2, V2. This is initial. Okay? It will be the momentum equal to the momentum final. Assume that there is a velocity here, then this object will move with its velocity, but its mass is M1 plus M2 multiplied by the final velocity without square. We have just one velocity for this mass. We don't have two velocities. We have an example of this. If we have in the weapons companies, they measure the velocity of the bullet. By doing this experiment, they use, I'll draw it here. They use a big box, wooden box, with two strings like this, and they send a bullet with a mass. I think there's an example. Yes. The next example, the next page, if the mass is equal to 0.005 kilograms, it's our bullet. It's easy to measure the mass of the bullet. Its velocity, V1 initially is equal to 300 meters per second. They know now the initial velocity. We have a box, and this box is stationary. It doesn't have any mass, so any velocity. Its velocity initially is equal to 0, but its mass M2 is equal to 0.995 kilograms. It is not 1 kilogram, it is a little bit by 5,000 because I need to make the calculations more simple. Okay? After this bullet goes inside this box, it will not hit the box and go back. It will go through inside the box or the block, and it will still inside it. And this system will move like this. Right? And the bullet will be here. They can measure the change in altitude, and they can measure the change in potential energy. They can measure the velocity of that block. We need to measure that velocity. By using this relation, the momentum initially is equal to the momentum finally. The momentum initially It's the first mass with its velocity. 0.005 multiplied by the velocity 300 plus the second. This is the system. The system contains the bullet and the box or the block. We need the total momentum initially. It is the momentum of the bullet plus the momentum of the block. Its mass is 0.995 multiplied by velocity 0. So the momentum initially is this multiplied by this. It will be 1.5. This is P initially with its units. P finally should be equal to P initially. Now we have one object, one velocity, one mass. So P final should be equal to P initial, which is 1.5. We don't need to deal with any direction. Which is equal to the total mass. It is 0.005 plus 0.995 multiplied by the velocity of the box with the bullet inside it. All of this is equal to 1, as you see. Divide over 1 or do anything, the velocity finally is equal to 1.5 meter per second. Initially, we have the velocity of the bullet, 300. When it met the block, the velocity later, 1.5. It's very small velocity. It's not just like this. Yes. 1.5 meter by a second. When the engineers in this company measure the altitude, the change of the change in Y, they can measure the potential energy, the change in potential energy. Then they can measure the work. Then they can change they can measure the change in the kinetic energy, and they can find the velocity. After that, if they don't know the initial velocity of the bullet, they can't find it. Okay? They can go from left to right or from right to left. It's okay. This is the way to measure the velocities of things. I computed also the kinetic energy before and after. Look, kinetic energy before or initially, it is equal to just the kinetic energy due to the bullet, because the box has zero velocity. In the last page, the kinetic energy 200 to 25 joules, and the kinetic energy finally is equal to, wow, just like that. Let me check it again. Just 1 joule. Yes, the first number is correct. The second number. The second number is correct. 1.125 joules. How much the change in kinetic energy? Delta K it is equal to the negative 223.8785. This is a work. This work, we lost all of this energy because the bullet changed the shape of the block in this place. Dig a hole. Also, there is a sound. There is a heat. There is a friction force. That's all for today. Any question? Tomorrow we will continue with elastic collision, and I think inelastic collision, and what we have also. We have the rocket problem. How the rocket had a force backward and inward. If you like, tomorrow I will start the review in the class or just record the videos. I'm asking now, do you need them as separate videos on each object, just like the first review? The first review, there is, for example, 2-3 minutes on velocity, 2-3 minutes on Newton's second law, and so on. You need to focus just on the subject. I will not do them in the class. I will just separate the subjects on each subject together. And I am sorry, I didn't put the homework of the work and the kinetic energy. I couldn't add just two problems to that homework. I create a new homework on potential energy and power, I think. Also, you have now the last homework on this material, which is 5 questions with 1 extra credits questions. That's all for today. Any questions online, offline? Okay, I'll close the meeting then and see you tomorrow. Thank you.